Good morning, boys and girls. Today we are going to talk about inverses, exponentials, and logarithmic functions, and review these topics from trigonometry pre-calculus and algebra 2. Let's start with inverses. Inverse functions. Inverses are where the inputs and outputs of a function have been interchanged. If you remember back in algebra 2 pre-calc, when we found the inverse, the first step we did was to switch the x and y, and then we'd solve for the y. Okay. Some things we should know about inverses, I guess notationally. When we talk about a function, we use f of x. But when I talk about its inverse, we say f with a little -1 like exponent. That means inverse. That is f inverse of x. And that indicates that we're talking about the inverse of a function. And then again on inverses, just repeating, again, the input and output have been changed, or the x and y hasn't been changed. So any point xy on the function would correspond to the point yx on the inverse. Okay? So again, we're changing all those things. So literally the points, every point xy has been switched and flopped. All xy's are being interchanged. Also that we should know that inverses are symmetric about the line y equals x. All right? So again, for instance, this is the function y equals x squared. Okay? Or at least for values that are greater than or equal to 0. And its inverse, the square root of x, would look like that. Again, these just to kind of, that's the square root kind of, I don't know, the quick sketch, it's not perfect here. But just to kind of show you that these are symmetric with the line y equals x. If I were to fold it over that line, they would match up. Okay? All inverses are symmetric with the line y equals x. Remember earlier on this week we talked about function being a function. Every input has one output. And we talked about, I'm going to test for that using the vertical line test, right? If I run a vertical line through this graph here, I know that it is a function. We can test if the function's inverse is a function, if these are going to be inverse functions, by using the horizontal line test. So in this case, if I run a horizontal line through it, hits twice. So this is a function, it's a quadratic, but its inverse is not. Okay? That is why back here on this example, that's why I had to restrict the domain just for x's are greater than 0. Okay? But we have inverse functions when both a function and its inverse are 1 to 1. Okay? All right. Now, let's also quickly talk about exponential functions and logarithmic functions. Okay, exponential functions are when x is now in the exponent. So like y equals 2 to the x or y equals e to the x are exponential functions. Generally speaking, we have either exponential growth or exponential decay. Exponential growth, again, looks like that. And exponential decay looks like this. Now you can reflect the growth and decay. You can, stretch it and shift it. If you do that, we would use our HK form to look something like this. Y equals A times B to the x minus H plus K. Where A is going to stretch or shrink your graph. B is the base, whatever base we want. But again, B must be greater than 1. And then, or between, well, I guess it's got to be greater than 0. And then the H again will shift your graph left and right, and the K will shift it up and down. And when we graph these, we should know that, the main points we use to help us sketch a graph of these is 0, 1. Doesn't matter what I plug in. When I plug anything to the 0 power, it doesn't matter what my base is. I'm always going to get 1. And then my base is then my next convenient point is 1, the base. So if I were graphing this, it'd go to the point, this being y equals 2 to the x. It'd go to the point 0, 1, and then 1, 2, since the base is 2. With ease, if your exponent is negative, that would make it a decay function. If the base is bigger than 1, it's growth. If the base is less than 1, it's decay. But still, it would go through 0, 1, and then 1, the base, and in this case, because the exponent's negative, it'd be 1, 1 over e, because it'd be to the negative first, so 1 over e. All right, so a couple points we would use to help us find and sketch our functions. Okay, very similar with logarithmic functions. Y equals log base 2 of x and y equals ln of x are two like logarithmic functions. Again, if you just have regular log, common log base 10, we just don't write log base 10. And if you have log base e, that is ln, we don't write log base e. Okay, quick little reminders there. If we're going to graph log functions, they would look something kind of like this. They have an asymptote at the x-axis, because remember, we can't take the log of 0 or a negative number. And then they kind of curve up. It's basically like an exponential growth on the side. If you have a negative in front, or if your base is less than 1, then it would look like this. Well, I guess that's a kind of a shifted one. Maybe more like that. But remember, they kind of run up and down the x-axis, or the y-axis. And again, we can use our HK form on these. Where again, A will vertically stretch or shrink your graph, the H shifts it left or right, and the K shifts up or down. And again, it doesn't matter what base we have on our log. All right? And then also don't forget our 3 rules for condensing or expanding logs. Again, we can go both ways with this, right? This would be expanding, going that direction, and this would be condensing, going that direction. But if you're multiplying the argument in a log, you can split it into 2 adding ones. If you are dividing, you can subtract. And if you have an exponent in the argument, you can move it to the front of the log. Also, quick review of change of base. If I wanted to evaluate log base 3 of 7, I could change the base to anything I want to. Most commonly, we use the common log, or ln. And I do like log of 7 over log of the old base. Log of the argument over log of the old base. So log of 7 over log of 3. And that's how we could evaluate how big log base 3 of 7 is. All right, so quick little review of exponentials, inverses, and logs. Again, if you got more questions, like I said, come see me. But real fast, let's do a few problems and review this. Okay, so for this first one here, we're given f of x equals 1 over x minus 5. And we want to find what is the largest possible set of points on which the following function has an inverse. All right, and so we could do this kind of analytically and just think about it, or if we know what this graph looks like, or we could actually go and graph it either by hand or on our calculator. But if I graph this, if you remember, there's a rational function where the bottom is 0, I've got a vertical asymptote. So I'd have a vertical asymptote at 5, and we have a horizontal asymptote. The degree of the top is less than the degree of the bottom, so at y equals 0. And I don't know if you remember, this is going to look something like this. If you don't remember how to graph this, you might want to go back and just review how to graph rationals. You can also graph that on your calculator, but it's going to look something like this. Now, the inverse will exist here wherever the function itself exists. Again, because you're just swapping those x and y's. And so this function exists everywhere. It has a domain of everything except for 5. So the inverse would exist everywhere except for 5, because at 5 we have that vertical asymptote. So the intervals, the large intervals we're going to have are going to be from negative infinity, that's a weird infinity, to 5, and then from 5 to infinity. It's a better infinity. All right, so that's where the largest intervals where the inverse is going to exist. All right, so next we actually want to go and find the inverse. So if I'm doing that, again, I would first replace my f of x with the y, just to make my life easy. And then to find the inverse, you're going to flop the x and y. So x equals y cubed. And now you're going to solve for y. If I take the cube root of both sides, I get the cube root of x equals y. Or now, when we write inverses, again, make sure you go back, use your inverse notation. And so I'd say f inverse of x, put that back in for the y, equals the cube root of x. So these are now inverses of each other. Also, remember, we could prove that these are inverses of each other if I were to plug one into the other. If I were to take the inverse and plug it into f, I should get x. And if I take f of x and plug it into the inverse, I should get x. That's a way to prove that these are actually inverse of each other. Both these things happen. I'm just going to do one of these here. But if I take f of x, or x cubed, blank cubed, and I plug in the inverse, the cube root of x, these should kill each other off and just leave with x, because inverses and functions like undo each other. So if I cube the cube root, hey, I do just get x, and that does work out. And it should work out the other way. You can go back and prove that yourself if you want to. But inverses in functions like undo each other's operations, and that's part of what makes them inverses. Okay, if I give you the graph of a function and ask you to sketch the inverse, you should be able to do that, again, using the fact that we know that this is symmetric about the line y equals x. So if I sketch that in, it would look like that. And now I want to think, okay, if I were to take this and just fold it over that green line, where would my graph end up? Well, my inverse would be, the function would start here and go something kind of like that. That's what the inverse would look like. So here we have f, and here we have f inverse. But you should be able to sketch the inverse from the function itself, using the fact that it's symmetric about the line y equals x. Okay, moving on to some log stuff. If I want to solve a logarithmic equation, log base 8 of x, remember the way that you are going to get rid of a log is by the inverse of a log. What undoes a log is exponentials, okay? So I'm going to exponentiate both sides with the same base. Okay, I'm making all this the exponent on a base of 8. And if I exponentiate that side with a base of 8, I've got to exponentiate this side with a base of 8. So now my logs kill each other off, and I'm left with just x equals 8 to the 1/3, or 8 to the 1/3 is the same thing as the cube root of 8, which is 2. So we get x equals 2. On log equations, again, you have to go and check your answer, because, again, you can't take the log of a negative or 0. In this case, 2 is not negative or 0, so I know I'm okay, and that is my answer. Okay, next, given log base b of x is equal to 0.36 and log base b of z is equal to 0.83, we want to evaluate log base b of x times z using our logarithmic properties. Okay, so what we're going to do is we're going to use our properties that allow us to expand this log. If two things are multiplying, we said earlier, we could write this as log base b of x plus log base b of z. Okay, and so what the point of this is just to practice these log rules. Now I know that log base b of x is 0.36 and log base b of z is 0.83, so I could add those together and we end up with 1.19. The whole point behind these problems, again, is just to practice those log rules. Okay, next, now we want to move on to exponential equations, and we're going to solve these. Two different ways we can approach this problem if I want to solve 2 to the x equals 55. One way to do this would be to use the inverse of logs. I mean inverse of exponentials, which are logs. And so I can take the log base 2 of both sides, and that would kill off my base of 2 and leave me with x. And so I get x equals log base 2 of 55. Okay. However, I don't think you're going to see that answer a whole bunch, because we can't really easily type that in onto our calculators. There is a way with the TI-84, but we're going to pretend like we can't use that. So what I'd have to do now is I'd have to use change of base. All right? And generally when we use change of base, just because ln is one less letter to write than log, we tend to use ln. And so I could rewrite this as ln of 55 over ln of the old base 2. So that is one way for me to get to the answer. Here's another way. And I think if you were to look into a textbook, I think this would be the more common way of the way they would show their work of doing it. Another way I could do this, I'm not going to really kill off the base. I'm just going to take the natural log of both sides so that I can use my log properties. Okay? And again, I'm going to use ln versus log just because it's one less letter. But now if I take the ln of both sides, I can use my log rule to take the exponent of x here and move it to the front and rewrite this as x ln 2 equals ln of 55. And now I can divide both sides by ln2, and I get the same answer, ln of 55 over ln of 2. Okay? Either way you choose to do this problem is fine, but we should all get to the same answer. Okay, boys and girls, that's all I have for you today. If you got more questions, again, please hit me up, text me, email me, message me. I'm here for you. Thank you very much, and have a great day.